Hi, the section 12.8, the diagnostics. So we have discussed some diagnostic plots in the linear regression and ANOVA, but I only introduced the minimal amount. So that I would like to enhance the diagnostics here. So this is important for statistical analysis. In the final projects also that you can include the diagnostics plot to justify your statistical models. So statistical procedures are almost automatic with statistical software, but the checking the assumptions, the doing diagnostics are essential part for statisticians. Yep, all regression and ANOVA analysis discussed in chapter 6, 7, 11, 12, and 13 are based on IID, independent and identically distributed sample. Independent means the two observations are not related, two errors are not related, and the identically distributed is the two errors have the same distribution. For example, the same size of variability. And the optimality of estimation relies on normality of errors. For example, we test the coefficient beta hat in a linear regression, and we use the beta hat divided by standard error of beta hat to test if beta is equal to 0. But for this test, this follows the t-distribution. But this entirely depends on the normal assumptions of the error term. If it's not normal, beta hat over S standard error of beta hat does not follow the t-distribution. So this depends on normality of errors. Yeah, so we have to ensure with careful diagnostics, these assumptions are met. And estimation is often valid without normality assumptions for large sample. While it is not optimal, still the estimator, for example, the beta hat obtained by X transposed X inverse X transposed Y. So this is still consistent and unbiased for mild the violation of assumptions. For example, if observations are not IID, the still beta hat is the somewhat a good estimator. Yeah, and I introduced several residual plots, and I introduced the R code for these later. Actually, these are almost automatic. So here is the kind of the simple plot. So at first, this is the residual versus the predictor. So since errors are IID, so it should not have any pattern. So we have the line that the error is equal to 0. Then errors are on average 0. So this line is the center, but also the residual should not have any pattern. So in this case, probably we can say that we have some tendency like this. So probably, okay, so we fit the Y on square footage for this case, but we have some curvature. So possibly the square footage square. So this may be useful variable to explain why. So residual versus predictor is the most basic, one of the most basic analysis that you should do to see if our model specification is correct. So if we have multiple predictors, you can check this for x1, x2, x3, and so on. So some packages that prepare the functions to generate the all pairwise plots for residual versus predictor, or sometimes the Y itself and the predictor. Yeah, usually the seeing residual is good because if the predictors are complicated, then relationship between Y and the predictor is more complicated. But residuals always have to be entirely random. So it's a good graph. And the next one is the fitted value versus standardized residuals. So the residuals, so basically this is the same. Sometimes this is standardized, so it's divided by some number. I will explain it later. And but the difference, the biggest difference is that the horizontal axis is for fitted values. So fitted values is, for example, if we have the actually the 4 predictors, beta 1 plus beta naught plus beta 1 times x1 plus beta 2 times x2 plus up to beta 4 times x4 in this case. So it's a kind of similar to the previous one, because at least this is a linear term of x1, especially if we have one variable. So this is just a linear function of x1. So it's probably almost the same as the previous figure, just slightly linearly transformed. So here, the fitted values are a mixture of these variables. So it's really hard to interpret when we see some curvature, but usually the most significant fact is that sometimes residual have some tendency, such as increasing variance as fitted value increases. So in this case, usually the variance gets larger when fitted value is larger. So if this happens, transform y. For example, y to log of y. Sometimes also you have to transform x. So suppose that x and y has linear relationship, but it's good when we have increasing variance of residuals, then we have to transform y into log y. Then if x and y are linearly related, then we also have to take logarithm for x. So it depends on the situation, but this indicates the necessity of taking some transformation, doing some transformation of y. Yeah, another reason that this plot is popular is that if we have multiple predictors, we can only make one figure to show this. If this horizontal axis is the predictor, we have to make multiple figures. So that is another reason. But to identify the relationship between response and the predictors, still the previous figure is essential. Yeah, here actually the y-axis, vertical axis is the standardized residuals. It's slightly different. And the standardized residual is defined as this. So basically, when we have residual epsilon I, we have to divide this by the SI. And SI is defined by the estimated variance estimated variance times 1 minus HII. And HII is the entry, the II's entry of the matrix XX X transposed X inverse X transposed. So this is called hat matrix, and actually the HY is equal to X beta hat. So basically HII represents the how much potential influence the observation makes to Y. So basically if we have X and Y, and the X values are not far away from the center, it has larger impact on the regression line. Okay, so think about the case that most observations are around the center, but one observation here and one observation here. Then these two observations have large influence on the regression line. Probably if we make a regression line that becomes here, because basically this point and this point determines the regression line. Otherwise, the squared error for these two observations gets larger. For example, even if we have more observations and this slope is flat, except for the two extreme observations. Except for these two observations, maybe the best line is here. But if we use this line, okay, so say L1, L2, if you use L2, then error for these observations becomes too large, so that the sum of squared residuals gets too large. So in such a case, actually the L1 achieves smaller the sum of residual squares. So that's why these 2 points are influential. So that means the residual for these 2 points are artificially low, because these observations affect the residual regression line itself. So actually it makes these 2 points makes the residual for these 2 points smaller. You can see the difference between the, distance between, vertical distance between L1 and these observations are really small. So in such a case, we have to account for that fact. So SI is smaller for these two observations. So we should have small SI so that the standardized residual gets larger. But anyway, so this is a technical adjustment for the residual. So usually the SI is, always the SI is larger when X values are far away from the center. Yeah. Next diagnostic plot is the Cook's distance. So Cook's distance means that the represents the how much each observation affects the regression line. So HI is called rivalage, HI or HII in the previous page, and HII is rivalage. So this is based on the value of X. So if the X value is far away from the center, it has potential to have large impact on the regression line. But the Cook's distance actually measures how much that observation affects to the regression line. Okay, so this data is some realistic data with 500 observations, and you can see the Cook's distance is larger for these observations. So that means actually, even though we have 500 observations, a few observations play a primary role to determine the regression line. So largest one, 0.25. And if we pick maybe largest 10, probably it's pretty large. It has the pretty large share in the total Cook's distance. So that is not good, because even though we have 500 observations, the few observations determines the estimation results. So Cook's distance quantifies the influence of each observation to the regression line by comparing the regression line by all observations and the regression line by all but ice observation. So to see the impact of the ice observation, we compare two things. The one is the regression line with all observation made by all observations, and the regression line made by all observations but ice observation. If these two have the large difference, that means the ice observation has a big impact to determine the regression line. So DI is basically the sum of squared residuals, yj hat and the yj hat superscript I. Yj hat superscript I is the estimate for J's observations, but that estimate is made without ice observation. Yj hat without any superscript is the usual estimate. So it uses all observations to estimate Yj hat. So this is just a normalizer. So it's the same for all i's, so it does not really matter. And the DI is defined by this quantity. So this is called Cook's distance or Cook's D. Yeah, this is common technique, so that we exclude one observation and see the impact on the estimation results. And the next one, I think that we have already covered in earlier chapters, chapter 4 or 5. This is a QQ plot that we would like to see the normality of the plots. If errors are normally distributed, then the QQ plot is the straight line pattern. So remember that the horizontal axis is the theoretical quantiles for errors, and the actual errors are on the y-axis. So, and both are ordered. The theoretical quantiles are ordered from the smallest to largest. So we have the about 500 observation in this case. And the standardized residuals are actual residuals, also ordered. So if everything is correct, then this should be the diagonal line. And this is standardized residual. So actually, this is the exact diagonal line. The y is equal to x. You can see scales are a little different. So 0 to 2 and 0 to 2. So probably this is the diagonal line. So if all observations are on the line, then we can say normal. The observations are distributed normal. But actually, we have some discrepancy here. Not too severe, but actually the error distribution, residual distributions are heavier than normal distribution. So slight violation to normal curve. And we cannot do many things to this figure. If the residual plots are more distinctive pattern, such as this, probably that we need transformation on y. And the other way around, so this is the convex curve, but the concave curve, if residual plot is like this, then we should have the transformation by the convex function. But this S-shaped, the residual, the normal QQ plot, we cannot do much significant things, but at least it gives a limitation to the assumption on error. So probably the t-tests are not as accurate. And also the model is a little less robust against some outliers. And those figures are made by just the plot of the linear object. Actually, if you type plot LM object, then the figures that I have shown appears one by one. So once you click the plot and you enter, then first plot appears, and you type the return key, then you will get another plot, and so on. If you want to get the specific plot, that you can specify the plot LM object, then which is equal to 1, 2, 3, and I think maybe 5 also, 1 to 4 or 1 to 5. So 1 is fitted versus residual, the 2 is QQ plot, the 3 is fitted versus standardized residual, and the 4 is for Cook's distance. You can use these for the final projects or any projects that which require the statistical diagnosis.